Every time you use an app or a website, you're interacting with something that is just unimaginably complex. And the real challenge for the people who build these things isn't just getting them to work, it's making sure they don't break. So how do they do it? Today, we're going to pull back the curtain on the clever strategies they use to hunt for bugs without getting totally lost in an infinite maze of possibilities.
Okay, to really get a grip on the size of this problem, let's just imagine a simple piece of software. It's got 20 different settings, right? And each of those settings has 20 possible options. If you wanted to test every single combination, you would have to run this many tests.
And to be clear, that number is it's beyond huge. It's way, way bigger than the number of stars in our galaxy. So trying to test every single one of those combinations isn't just a bad idea, it's literally physically impossible. There's just no way. Which leads to the big question, right? If you can't test everything, how does any piece of software ever get released without just falling apart all the time? How do you find the bugs that actually matter? Well, the answer isn't about working harder. It's about working smarter. So one of the first really logical ways people tried to tackle this puzzle is a technique called cause-effect graphing. The whole approach is to basically think like a detective and map out all the logical clues one by one. The main idea here is to treat the software like a black box. You don't really need to know what's going on with the code inside. All you care about is what goes in and what's supposed to come out. And it's actually a pretty great approach, especially for smaller, more self-contained programs. In the concept itself, it's really simple. You've got causes. These are your inputs. Think of a user clicking a button or typing something into a field. And then you've got effects. These are the results, the outputs, like a record getting saved, an error message popping up, or a brand new window opening. Simple. So let's say you're testing a form. A cause could be the user selecting married from a drop-down menu. Another cause is them typing a number into the number of children field. The effect we're hoping for is that the record gets updated. But wait, what if they select unmarried but also enter 3 for the number of children? Well, that doesn't make sense. It's a logical contradiction. And that's what the graph helps you figure out, so you can trigger an error message, a different effect instead. But here's the catch. This is where the whole thing kind of falls apart. For a simple form, it works great. But for a modern app with hundreds of inputs and thousands of possible results, that graph just becomes a tangled, unmanageable nightmare. It just doesn't scale up. So to get around this huge scaling problem, testers needed a strategy that was way more powerful and efficient. And this brings us to the hero of our story, pairwise testing. Now, I want you to pay really close attention to that one keyword, pair. See, instead of trying to test every possible combination of all the inputs at the same time, this technique focuses on testing every possible combination for each pair of inputs. It's a small change in wording, but it's a revolutionary shift in thinking. And this whole thing works because of one big, powerful idea that's backed by decades of data. The huge majority of bugs aren't caused by some crazy weird interaction between 5 or 6 different settings. Nope, they're usually triggered by a single faulty setting or the interaction between just 2 of them. All right, to really see the magic of this in action, let's check out a practical example. Let's imagine we're testing a pretty basic settings window inside an application. So on this screen, we've got 4 pretty standard controls. There's a list box with 10 items, a checkbox that can be checked or unchecked, a radio button that's on or off, and a text box where you can type in any number from 1 to 100. Doesn't seem too complicated, right? Well, let's see what happens when we actually try to test it. First up, let's try it the old-fashioned way, exhaustive testing. This means we're going to create a separate test for every single possible combination of these 4 controls. So you multiply the options together, that's 10 times 2 times 2 times 100, and you get this, over 4,000 unique test cases. And that's just for this one tiny, simple screen. That is a ridiculous amount of work. Okay, now let's switch gears and apply the logic of pairwise testing. We don't need to test every single combination. We just need to design our tests in a smart way so that every possible pair of options gets tested at least once. For instance, we need to make sure the list box's first option gets tested with the checkbox being both checked and unchecked. And the result is, well, it's amazing. By focusing only on the pairs, the number of test cases absolutely plummets from over 4,000 all the way down to about 25. That's it. This right here is the magic of pairwise testing. You get incredible coverage for the most likely bugs, but with just a tiny fraction of the effort. But of course, no technique is ever perfect. And while pairwise testing is incredibly powerful, it's really important to understand where it works best and, well, what its limitations are. The good stuff? Well, the advantages are huge. You're running way fewer tests, which directly saves a ton of time and money. But here's the best part. You're not really sacrificing quality. By zeroing in on these high-risk pairs, you actually get more efficient at finding bugs. You catch more of them with less work. It's a win-win. But yeah, there are trade-offs. By its very nature, this method might miss a really rare bug that only shows up when 3 or more specific settings are combined in some unique, weird way. And its success really depends on the testers choosing the right inputs to test in the first place. If you don't really understand the parameters you're working with, the technique just won't be as effective. This quote really just sums it all up perfectly. The goal isn't to be exhaustive, because as we saw, that's impossible. The goal is to be effective. It's a strategic bet that almost always pays off. So the real takeaway here is this. Building reliable software in the world we live in today is a game of strategy, not stamina. It's about intelligently figuring out where bugs are most likely to be hiding and focusing all your energy right there, instead of just trying to search everywhere at once. And that kind of leaves us with a final thought. The next time you're using an app and it works perfectly, or maybe the next time it crashes on you out of nowhere, just take a second to think about it. It probably wasn't a single setting that caused it, but a very specific hidden interaction between two of them, a pair that the testers either brilliantly caught or narrowly missed.